Hello, Physics 1 people. I'm here with another video applying energy, and we'll also apply torque concepts to a rotating object. In this case, we're going to have an object rolling down a hill, and it's going to roll without slipping. So as usual, that assumption is going to help us. So I'm going to write this out, and I'm not going to tell you what it is. If it's a sphere, if it's a disc, if it's a ring, if it's a cylinder, I'm not going to tell you. I'm just going to assume that this has some moment of inertia I, and it has some radius r. And that's all we're going to work with. And we're going to go ahead and let this have some incline theta. Okay, rolling without slipping. So we know from everyday experience that this is going to kind of rotate in a counterclockwise fashion. So we're expecting a positive angular velocity and a positive angular acceleration. Our rolling without slipping condition is going to relate the motion, the angular motion, with the velocity along the hillside. Now, we have to choose coordinates for the hill. Whenever we can, we want to choose coordinates so that the linear acceleration is really simple. So in this case, I'm going to choose up the ramp to be positive x. I'm going to choose down or perpendicular to be positive y. And what that means is that my acceleration is actually going to be in the negative x direction. So when omega is positive, I'm going to have a negative velocity. So the rolling without slipping condition tells me that r omega equals minus velocity. And when I say velocity, I'm talking about velocity in the x direction along the hillside. And similarly, r times alpha will equal minus the acceleration in the x direction. And the acceleration in the y direction, into the hill would be 0. That's just trivially true. So this rolling without slipping condition is going to help us both with the energy and the force torque analysis. Okay, so the goal is to find an expression for the acceleration down in the x direction, so the acceleration down the ramp. Let's start with an energy analysis. Okay, so I've got my hillside, I've got a wheel, and the energy analysis starts as it always does. We have to define the system. So we're going to say the system equals the object and gravity. So that's fine. That's going to account for all of the forms of energy. So there's going to be no outside force which acts and does work on this, it turns out. So the work energy theorem, which says the work equals the change in kinetic energy plus the change in potential energy, well, the work is going to be 0. So that's going to be simple. Let's go ahead and, I should have said this before, let's assume that the initial velocity was 0 just to make the arithmetic a little cleaner. So we're going to assume it all starts from rest. In which case, the work energy theorem tells me, just kind of moving over here, that 0 equals the final kinetic energy, so that's going to be 1/2 the mass times the velocity in the x direction squared, plus 1/2 I times omega squared. These are the final velocities. The initial velocity is 0, so minus 0, plus the change in potential energy. So that's going to be plus mg times delta, I'll call it h, the height. Remember, so as it falls, gravity acts up and down. So the potential energy due to gravity cares about the vertical distance, not so much the distance along the side of the hill. And that's okay, because we can, if I use my angle theta, I can actually say that the distance delta x, I can relate delta x to theta and h by saying the sine of h, sorry, sine of theta is h over delta x. Therefore, delta x equals h divided by sine of theta. Okay? Or, turning it around, h equals, I don't know why I wrote it that way. This is the better way. There we go. So let's turn this all around. I can write omega as velocity over r, and let's worry about minus signs. If omega is positive, the velocity is negative, so there'd really be a minus sign there, even though it's not going to matter when I square things. And I end up with the following expression. I have 0 equals 1/2 the mass times the velocity in the x direction squared, which would be x velocity, plus 1/2 I velocity in the x direction squared over r squared plus mg sine theta times delta x. And I can rearrange that and solve for velocity squared. So I get the velocity squared in the x direction equals, well, first of all, I'm going to move this gravitational term over. So that gives me a minus mg sine theta times delta x. And I'm going to go ahead and, oh, okay. And then I can factor out the velocity squared. So the coefficient of that is half m plus half I over r squared. So I can divide this by half of m plus I over r squared. And let's just clean this up just a tiny bit. So I can see that vx squared equals, divide top and bottom by m, move the half around. This is minus 2g sine theta delta x divided by 1 plus I over m r squared. And using the fact that from kinematic equation 3, since it starts from rest, I know that the final velocity squared should equal twice the acceleration times delta x, the acceleration in the x direction. I conclude that the acceleration in the x direction equals minus g sine theta divided by 1 plus I over m r squared. That's kind of a curious result. This combination I divided by mr squared, well, that's kind of an interesting combination. If you think about a few examples, you'll note that I, for simple shapes with only one length scale, so simple shapes of revolution, is always some number times the mass times the length squared. So when we write I over mr squared, that's actually, it's isolating the numerical coefficient. So that's isolating just the number. And this is the same for all shapes of the same type. Not shapes, for all objects of the same shape. Sorry. Not this all day here. For all objects of the same shape. So for example, all disks, all solid disks all have a moment of inertia, which is, say a solid disk is 1/2 mr squared, so the number equals 1/2. For all hoops, the number would equal 1. For all solid spheres, solid spheres, if I remember right, is you're going to have the number equal 2/5. So whether it's a large sphere or small sphere, if they're both solid spheres, they should tie. Whether it's a large hoop or a small hoop, they should tie. Whether it's a large solid disk or small solid disk, they should tie. But different shapes won't tie. So the one with the larger of the coefficient will have the smaller acceleration. So we would expect a solid disk to win when compared to a hoop or a hollow disk. So that's kind of an interesting observation. Let's analyze the same problem from a force point of view, and we will get the same answers, unsurprisingly. So from a force / torque perspective. Well, let's start with a picture. We have a ramp. We have an angle theta. We have an object with some moment of inertia. And well, let's think about what are the forces at play here. So there's no slipping. If there's no slipping, well, there must be something which keeps it from sliding. There must be friction. So we're going to have friction acting up the ramp. It's going to be static friction because it's not sliding. So you have static friction going up the ramp, which is actually what causes the wheel to turn. And then there's a center of mass. We're going to have a weight acting down. So we have static friction and weight. And then also, I'm going to shift it over here. We're going to have a normal force. Oh, I'll just say it there. There's a normal force. So let me redraw all of that in a little bit better form. So I'm going to have my object here. Because I'm interested in torques, I'm going to keep it extended, so it's a larger object. I'm going to draw the lever arm here. 1 radius. There is a friction force. There's also a normal force. So I want to change colors just so it's really clear. I'm afraid that everything's going to kind of pile up. We have a normal force. And then we also have a weight. Change colors yet again. Make that blue. Sorry, just trying to clean this up a little bit. So I'm going to have a weight acting down. And then I have a normal force in green. Acting that way. Okay, so it's a little complicated to analyze. Let's make some observations though. Fact, having done all that, let's make it even larger. Why struggle with something so simple? Let's save our struggles for hard things. Let's make it larger. There we go. Now we've got a chance. And at the point of contact, we're going to have a friction force, and we'll have a normal force. And then at the center of the wheel, we'll have the weight acting down. Okay. Well, we're still going to choose X and Y in the same direction. So we're going to choose X to be up the ramp. We're going to choose Y to be perpendicular. In which case, we want to break the weight into components parallel and perpendicular as before. So F net in the X direction is going to be minus mg sine theta coming from the weight. And then I'm also going to have a positive force coming from the friction, because up the ramp is what I'm calling positive. And that should equal the mass times acceleration in the X direction. In the Y direction, I have F net in the Y direction. And that's going to be, well, there's a normal force in the Y direction. I also have the weight in the Y direction. So I get minus mg cosine theta from the weight plus the normal force. And that has to add up to 0 because the wheel doesn't tunnel through the surface. And now we come to the torque equation. So I'm going to go to the next page on that one. So let's study rotations about the center of the wheel. The weight provides no torque. So the torque to the weight is going to be 0 about the center of mass, right? The center of the object. So I don't worry about torques due to that. We have a normal force and we have a friction force. Well, the torque due to the normal force will also be 0 because the angle between the lever arm and the normal force is 180. And when you apply the formula for torque, you have the sine of 180, which is 0. So, or you can just see it that the normal force doesn't cause any twisting. It just pushes along the radial direction. So in fact, the only force which gives rise to any torque is the friction force. I see that the friction force is going to create a positive torque because it makes it want to rotate in a counterclockwise fashion. So I'd say that is going to be the radius times the friction force. And then the angle between them is 90 degrees, so I just have the sine of 90, which is 1. That must equal I times alpha. Or if I use my rolling without slipping condition, I get R times F equals I times the acceleration over R. Now let's be really careful with minus signs. If alpha is positive, the acceleration is negative, so I actually get a minus sign there. Or the friction force equals minus I over R squared. There's that combination again, times the acceleration. So if the acceleration is positive, the frictional force will be negative, and if the acceleration, or actually what in this case, we know the acceleration is going to be negative because it's going to be down the ramp, in which case the friction force will be positive up the ramp. Let's look back at our previous equation. The previous equation related the friction force to the acceleration along the ramp. And we've got a new equation which relates the friction force to the acceleration along the ramp. I should label these with an X. and I want to solve them simultaneously. So my equations are, from the force equation, I get mass times the acceleration along the ramp equals the friction force minus mg sine theta. And from the torque equation, I get the friction force equals minus I over r squared times the acceleration in the x direction. So substituting this in and regrouping, I get the acceleration in the x direction equals, it's going to be minus mg sine theta divided by m plus I over r squared. That should start to look kind of familiar. I'm going to divide top and bottom by the mass and write the acceleration in the x direction equals minus g sine theta over 1 plus I over m r squared. It's the same. Ta-da! Well, no surprise really, because of course all of our rotational equations just came, and even our derivation of energy conservation started with Newton's second law. So there's no surprise that you can always apply it and get to the same result. Okay, so that describes how objects roll down a ramp, and the key points are, or the key results, all objects of the same shape have the same acceleration down the hill. That's the first point. Second point, in a race between different shapes, the one with the smaller number, which equals I over mr squared, will win. That kind of makes sense, because if this number is larger, the moment of inertia is larger, which means that it's harder to make the object twist. So that kind of intuitively feels right. Okay, that is my last video on combining rotational motion with accelerations. I want to post a couple videos discussing equilibrium and when things tip, and that will wrap things up for the semester.